hope you're having a great day. This is going to be my lab report for the second lab that we're supposed to do, motion of a falling object. Now, just an introduction to what we're supposed to be doing here. What we're doing is we're going to drop an object from rest at a height, approximately 1.5 meters, something like that. That's what I'm doing. And we're going to compare that data with two computational models that we code in GlowScript. Right? I'm going to get into more details with that later on. For now, let me just describe the initial conditions I'm using. I'm just going to use a crumpled up piece of paper. The initial position will be 0 since it's starting from rest, and the vector position is only in the y-axis, right? So 0, -1, 0, that's the sort of general unit vector where it's traveling. Now, what's the fundamental physics principles that are at play in this experiment? Obviously, the base principle is Newton's second law, right? It's crucial to this lab, it was crucial to the previous lab, and it's used a lot in our computational model. And all it states is that the net force of an object equals the change in momentum over the change in time. And from this, we get our velocity update formula, which we use in our computational model. But what's new here? It's the force of gravity. So Fg equals mg, that's the Fg equals mg. That's one of the equations you can find. That's one of the equations for finding gravity. I've given both equations for f grab here. And this one's going to be used in our computational model. But far more importantly, I think, is this drag equation right here. And this negative v coefficient, this whole equation, negative b times the magnitude of v squared, we're going to use this in our computational model when we implement the effects of both gravity and drag. So now let me get into the details of the experiment, right? What are we doing? I'm going to use a crumpled piece of paper, like I already mentioned. Gravity and drag are going to be the only sort of surrounding variables at play here. Our observed result is going to be recorded using Tracker. Now we're going to make two experimental models in GlowScript. One will have only the effects of gravity, while the other will have both the effects of gravity and drag. So that's essentially the experiment that we're doing here. That's the dichotomy, that's the difference. So the initial assumptions that we're going to do for our observed data is that the paper will begin at exactly 0 on the y-axis, and the paper will start with 0 velocity, and that there are no other forces on the system in gravity and drag. So you can see here I've carried out the experiment. We have a rough graph here. You're free to ignore the one at the top. That's the x-axis. We don't care about that. But we have this graph here for the y-axis, and I'll plot this a little more formally in the next slide. But you can see I've done the experiment here. And this is a bit more formal sort of in Microsoft Excel. I've plotted the observed results that we got from Tracker. So now moving on to the interesting part, right? The computational models. So our first computational model incorporates only gravity. So you can see here that the drag coefficient b is 0. What am I doing here? I'm using minus ball dot m mg in order to calculate this sort of f grab value. And for now, I'm not using fnet. I'm using this new separate variable f grab in order to update my ball velocity. Right? It's just easier this way. I could have just done this in fnet. It doesn't really matter. But yeah, it's just easier this way. And you can see other than that, there's not much that I've changed. This t value was calculated using the value that I had in Tracker. And with this code, this is the graph that I got. So you can see here, travels about minus 0.8 meters. That's the estimated travel. But now on to the second computational model. We have both gravity and drag. Note here that I've calculated the value for b to be 0.0004 for this particular piece of paper based on its own weight, etc., etc. The t value remains the same. T value remains the same, of course, but here you can see I've made some changes. I've gotten rid of the f graph variable. I'm just using fnet now. But you can see here I'm using the drag equation, right? B times the magnitude of v squared. So you see what I'm doing here, right? I'm just using the drag equation that we discussed in the the fundamental physics behind this experiment to keep updating my ball velocity in order to get this computational model here. And this is the end result that we end up with. This is the graph that we end up with. Now comparing all three graphs, right? Our observed data to the drag graph and the gravity graph, you can see, interestingly enough, the observed data is the one that actually travels the furthest. And the one that travels the least is drag, is our drag model, which I guess you'd expect. And in the middle, we have our gravity only model. Now, some explanations for why there may be a possible error or deviation within this. It's important to note that Tracker is kind of inaccurate and arbitrary, right? Because you're manually tracking things in there. There's very few data points. You're going frame by frame. So there's a lot of room for human error in there. So that's one big reason, right? But the second big reason is that there may have been other forces acting on the paper that I didn't necessarily incorporate in the experiment because we're not supposed to, right? It's a pretty simple experiment. So for example, a light draft acting on the paper, that I can't do anything about that, but that might have been a potential cause of error in this experiment. Now onto the final two questions. What does it mean and what if? Which models predict a terminal velocity? That would be the one with drag, right? Because the entire definition of terminal velocity is that the force of gravity points down and equals the force of drag pointing up. That's what terminal velocity is. So the model with drag fulfills this prediction the most. But now for the what if question. If the object was thrown downward with an initial velocity, would the terminal velocity change? And the answer is no. The initial velocity is irrelevant because only the drag and weight matter for the ultimate terminal velocity of the object, right? So no, the terminal velocity would not change even if we threw the object down. Thank you very much for coming through this lab with me. I hope the results were satisfactory. Have a nice day.